Hello students, this is Dr. Diaz and let's talk about chemical reactions, the best part of chemistry. Let's make some explosions, just kidding. In a physical change and chemical change, this is important part to understand and see the difference between both. In a physical change, the chemical composition of the substance remain constant. Example of physical changes are the melting, physical or boiling point. So if I have a frozen water, so I have ice, but it's still water, right? It's a solid water. If I have liquid water, it's still water. If I have vapor water, it's still water. So I'm not changing the chemistry part of the water, okay? But in a chemical change, the chemical composition of the substance change, like in a combustion. So, or rooting of fruit, could be banana, pear, whatever. And the rusting, that is oxidation happen over here. Then digestion as well. So during chemical reaction, a new substance is formed. Process in which a substance or substances transform in one or more new substance is called chemical reaction. And we can see evidence for chemical reactions, right? So there are 4 observations that indicate a chemical reaction is taking place. For example, gas is produced. And then how are we going to see this? Because you're going to see some fizzing or half bubbling. So the release of hydrogen like we have here. We have a magnesium and this is a solution of acid. So the reaction here is happening and are producing hydrogen gas over here. See the bubbling over here and the gas going up. So that is evidence of a chemical reaction. Another evidence could be formation of precipitate or no soluble solid that is produced in a solution. So a substance dissolves in water to give aqueous solution. If you add 2 aqueous solutions together, we may observe the production of solid substance. This we call precipitate. If you have no soluble solid, we call precipitate. Sometimes you're gonna make reactions that appear some like cloudy, like a milk, for example, and this is like, oh, is this a precipitation? Yes, that is a precipitation. That is a microparticles. That is a powder. If you let time, that will settle down, and you're gonna see that is a solid precipitate on your bottle or your tube. A permanent color change is observed. So many chemical reactions involve permanent color change. You can see here have a yellow substance and a no color substance over here. When they are together, see forming a different color, like a red color over here. And if it's a permanent, that is evidence that we have a chemical reaction happening over there. If you don't see anything of this, maybe you can feel heat or the tube is getting warm or getting colder. That is energy change observed. So a reaction that releases heat is an exothermic reaction. And a reaction that absorbs heat is an endothermic reaction. In this case, if you touch the beaker, you're going to feel very warm. So the beaker is getting warm. That is exothermic reactions, releasing heat, okay? So here in the graphic, you can see the endothermic reaction. I have more energy in this side because it's absorbing energy to produce the product C. Here, so the energy here is greater and for the reactant. So in that the energy decrease in the product, that means that releases energy to produce C. So a chemical equation describes a chemical reaction using formulas and symbols. A general chemical equation is like this. So we have a reactants and we have the products. So and also we specify the physical state of the reactants. We have solid, liquid, gas, and aqueous solution. I'm pretty sure that some of you that never had the chemistry at the high school before, it's asking yourself like, what is the difference between liquid and aqueous solution? So aqueous solution is a solution that we have some liquid dissolved in water, like for example hydrochloric acid, hydrosulfuric or sulfuric acid, right? I said hydro, I'm sorry, sulfuric acid. So this is aqueous solution. However, liquid could be water. That's a liquid, okay? So let's go to another example over here. Here we have a reaction. So here we have the reactants, and here have the products. And this number here there are the coefficients, stoichiometric coefficients. Those number tells you the number of the molecule that we have over there, or the compound. So we have here one molecule of hydrogen. I have a half of oxygen, and I have one molecule of water. And this over here, the subscript. This is the what tells you that we have water. That is the soul of the substance. So you cannot change those subscript over here because this is completely different from this, right? This is peroxide and this is water. So they are complete different substances. And why you don't change this? Because of this, because you change the substance. Okay, you change the chemical composition of the substance. And what is the difference between this and this? Let me explain with the example. Very simple example. Imagine if you have a compound that is phases. So I have two eyes, and I have one nose and one mouth. So imagine if I have to draw this, and they say to you, so I have two of this. But as another student says, like, okay, so if I need to multiply all this to tells you the number of atoms, can I write like this, 4 and 2 and M2? Let's see the difference. So if I have a two-phase with two eyes, so I have over here two eyes, and I have one nose and one nose, so 2 and 2 is a 4 eyes separated, and I have two nose, and I have one mouth here, one mouth here. So I have a two-phase. But here, look at this. They're all together. So it will be like this. So I have 4 eyes, 2 nose, and 2 mouths. See, they're complete different monster. So we cannot mix it. So we cannot change the subscript. Okay? And also we have the state of matter over there, indicating gas, and liquid. So that is another other symbols that we use in the reactions. We have the arrows, that means separate the products and reactants. And we have the plus sign that we use to add, or like react with, add to, plus. And this small triangle over the arrow is indicating that you're using heat as a catalyst. And here we use iron as a catalyst. When you see NR, that is no reaction, and here are the states that you already know. So let's look at this chemical reaction, and just a reminder that it's very important to learn the nomenclature and how to write the formulas, because sometimes we can use a text to indicate the reaction, and you have to write down the reaction, like here. Aqueous acetic acid is added to solid sodium carbonate, yielding aqueous sodium acetate, liquid water, and carbon dioxide. Okay, so here the text is describing everything, the compound and the state. Okay, who is the reactants and which one are the products. Very important. Some elements, we have 7 non-metals elements that occur naturally as diatomic molecules. So if you look at the periodic table, and you're going to see that 7 makes 7, so we have nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All those elements plus hydrogen, they are never by itself. And you could say like, oh, I already saw oxygen by itself in the molecule. Of course, but it's not by itself. They are connected to other elements, like here in water. Okay, they are bound. They bind with the hydrogen. So oxygen is bind with the hydrogen. Okay. So here, as I said, so we have diatomic molecules. Just repeating because this is very important. If you have a text to describe you react with hydrogen, you will not write hydrogen by itself. You're going to write H2. Okay. And again, we change the coefficient, we change the amount of the molecule. So I have 2 water molecules over here. But if you change the subscript, you change the composition, the density of the substance. Okay, you don't change that. So when you write a chemical equation, the number of atoms of each element must be the same on both sides. That means if I have a 2 carbon and a reactant, I must have a 2 carbon and the product. It doesn't matter who the carbon is bound with. Okay? So we balance chemical reactions by placing a whole number coefficient in front of the substance that are deficient. So a coefficient is a multiplier. So I can say that I have 3 times 2 is 6 hydrogen and I have 3 oxygen, because this means that I have 1, 2, 3 water molecule. Okay? So how are we going to balance chemical equations? It's at the beginning can be really hard, but it's fun because it's like a game. So you need the same numbers of the atoms that you have on one side must have the same numbers that you have on the other side. Before placing coefficients in the equation, first you check the formulas are correct. Never change the subscript, as I said before. So you're going to balance each element equation, start with the most complex formula. And then you balance polyatomic ions as a single unit. That means if I have a phosphate like this, I have a 3 phosphate. If on the other side I have just 1 phosphate, I need to multiply that. Okay, because I'm going to have 3 and 3. So I'm going to count as just one element. So the coefficient must be whole numbers. If you get a fraction, multiply the whole equation by the denominator to get whole numbers, like here. So sometimes it's easy to use a fraction to balance equation. So the way that you're going to do is exactly what I did here. So you multiply the whole equation and for 2. So I have whole numbers at the end, right? So after balance equations, you're going to check if there are the same numbers of atoms of each element or polyatomic ion on both sides. So I have 4 hydrogen, 4 hydrogen. I have 2 oxidants, and I have 2 oxidants on this side. So it's completely good and fine. Finally, check that you have the smallest whole number ratio of coefficients. If you can divide all the coefficients by a common factor, like here, look at this, I have 2, 2, and 4. You can divide it all by 2. You're going to do this. So to complete your balancing of the reaction. So you can balance this. So I will ask you to pause the video and then do by yourself. So I encourage you to make a table. Put the reactant on one side and product on the other side. So I have alumina on this side. I have barium, and I have a sulfate, and I have nitrate, right? So alumina I have 2, barium I have 1, sulfate I have 3, nitrate I have 2. So on the other side, I have 1 aluminum, I have barium, I have 1 as well, sulfate, I have 1, and nitrate, I have 3. So if I start with the aluminum over here, I'm gonna put a 2 over here. So I like to use something that I call matcha rule. So I start with the metals, and then I go to non-metals, and then I go to carbon, and then I go to hydrogen, and then I go to oxygen. Oh, okay. So here, if I fix aluminum over here, now I have this. This is done. So I have 2 and 2. But now, look at this. 2 times 3 is 6. I have 6 nitrate. While here, I only have 2. To have 6 nitrates on this side, I can put a 3 over here, right? So 3 times 2 will be 6. 6 nitrates, so this is fixed. But now I have 3 bariums over here, so I will fix the barium as well. So gonna be 3 and 3, so they are fixed. So now I have 3 bariums, but now I have 3 sulfates. So So here I have a 3 sulfate. So now it's well balanced in both sides. Good? Perfect. So let's practice a little bit more. So we have those reactions. I would encourage you to pause your video and try by yourself. So if you need more time, just press pause, okay? So we have 2 nitrogen and the reactant side. So make tables. Make tables that, like one side is reactant, the other side is product, put the elements. That is the easiest way to not make mistakes, okay? So we have 3, but now I have 6 hydrogen and 6 hydrogen. It's all balanced, all the elements. Here are the same thing. I have 6, and here I have 6 sodiums. I have 2 phosphorus. I have 5 over here plus 3, right? So I have 3 oxygen plus 5 are 8. So 2 times 4 is 8. So I have 8 and 8. So all perfect. C, and then we have the letter D. So here you have this P2O7. You're gonna take consideration as one single element. So in the one side I have, look, I had before one element, one of this, and here I had 3 of this. So it will be simple. That's why I started the 3. So I fixed over here, and then I start to fix the others. So I have 4 aluminum over here, so I went to 4 over there as well. And then I fixed the hydrogen and oxygen. Okay? One more. This one I use to give an example where it's easy to use fractions. So I have reactants and product over here. So I have carbon, hydrogen, oxygen, carbon, hydrogen, and oxygen. So I have a 2, I have 6, and I have 2. And the other side I have 1, I have 2 hydrogen, and I have 3 oxygen, right? So now I will start with carbon, so I can put a 2 over here. So now it's fixed, but now I have 4 oxygen on this side. So 4 plus 1 will be 5 oxygen. But now I will look to the hydrogen. So hydrogen I have 6. And in this side I only have 2, so I'm going to put it over here 3. Oops. 3. So 3 times 2 is 6. So now I have 6 and 6 and 2 and 2. But now I have 3 plus 4, which makes 7. So I have 7 oxygen on this side and 2 on the other side. So the easiest way when I get those kind of numbers is use a fraction. Because I know 7 divided by 2 multiplied by 2 is 7. So it will be well balanced because I will have 7 on this side and 7 on the other side. But I need whole numbers, so I'm going to multiply my whole equation by 2. So I'm going to have a 2C2H6 plus 7 oxygens giving 2 CO2 plus 3, with 4 over here. And 3 times 2 is 6, 6 water molecules. Okay? Good? So now let's talk about classifying chemical reactions. We have 5 types that we're going to discuss here. So combination reactions, decomposition reactions, single replacement reaction, double replacement reaction, and neutralization. So double replacement, single replacement, I also call it displacement instead replacement in most of the books, okay? So combination, also called a synthesis reaction. It's a reaction in which simpler substances are combined in a more complex. So we have 2 or more substances, and then you produce only one substance. Okay? So we have a metal plus oxygen gas, so we're going to produce a metal oxide. See here, we have the heat symbol, so we are using the heat as the catalyst over here. So I have a video here to show you magnesium reacting with oxygen.
A little slower developing physically than most other kids. Sitting up,
Oh, sorry. I'm trying to, here we go. So we are using heating. So heat is to accelerate the process. It's not reacting with the metal in this case. So there's oxygen is around the metals reacting with. So now you see a very white, bright light. And at the end, you're gonna see a very white color final product. Actually, that's a powder if you touch that. So he will not touch because it's hot, but will convert in powder. So that is magnesium oxide. Okay. Um, so that is a good example of the reaction. So we can react a non-metal with the oxygen and gas. So we're going to produce a non-metal oxide, like we have here, sulfur with oxygen, producing SO2. So sulfur dioxide is a greenhouse gas, right? So a metal and non-metal react with a combination reaction to give an ionic compound. So we have metal and non-metal, like you here have a lithium and bromine. So we produce lithium bromide. That is metal and non-metal. We have ionic compounds over here. So the decomposition reaction is opposite of the composition reaction. So in a decomposition, a single complex compound is broken down into two or more substances, like you see here in this example. So heat is often required, as in the composition or synthesis reaction, to start the reaction. Okay, let me grab my pen again. So example of heating solid mercury oxide, set mercury 2, remember that. So just use this unit also to review nomenclature and how to write your formula. So here we have this breaking down and the mercury and oxygen, and here we have a calcium carbonate decompose and the calcium oxide and carbon dioxide. And here I have a reaction to show you as well for the decomposition reaction. A very cool one is the decomposition of sugar, which is great.
Metal carbonate decomposes to give carbon dioxide and the metal oxide. We will heat a sample of copper 2 carbonate. As we heat the copper carbonate decomposes to give a characteristic flat copper oxide. The carbon dioxide that is released is bubbled through lime water. The lime water is a solution of calcium hydroxide. The carbonic acid and the calcium hydroxide react to produce calcium carbonate, which is insoluble. The lime water turns cloudy because the carbon dioxide, as it bubbles through the water, produces carbonic acid.
See, that is the type of the reaction that I said. You see cloudy like in milk. That is a precipitate. So that you see little powder, you can see little small, very small particles over there. But some students, when look at that in the lab, says like, oh, is that a precipitate? Yeah, that is a precipitate. That is a very small particles that after minutes or sometimes long minutes will settle down into your tube. So when a metal undergoes a single replacement reaction, it displaces another metal from compound or aqueous solution. But the metal that displaces the other metal does because they are more active than the other one. So the activity of metal is a measure of its ability to compete in a replacement reaction. And it's like in the prom, if you are dancing with some girl, or if you're dancing with some man, and someone come and take out your pair and replace your pair, shows that the other one is more active or more stronger than the other one, right? It's the same here. So it's a single displacement. So someone will be always by itself on both sides of the reaction. So on the one side is one element, the other side is another element. So you can see that it's a single replacement. So here we have the activity series. So you can see like lithium is very strong, so we replace all the elements over here. And cold is very weak, will not replace anyone. So that is a table that you can use in the single replacement reaction. So it's a reaction in which a more active metal displaces another less active metal in a compound. And a very good example here is this reaction over here. Very nice to see it.
In the single displacement reaction of a metal replacing a metal ion from its compound, a more reactive metal will displace a less reactive metal from its compound. We have a solution of silver nitrate, and we're going to add some copper wire to the solution. The copper is a more reactive metal than the silver, and the copper metal will replace the silver ion from its solution. As the reaction occurs, silver metal will form on the copper wire. After about 30 minutes, we see that we formed a very large amount of solid silver crystals. The solution has turned blue due to the formation of the copper plus 2 ions.
So see how that works, and beautiful to see it, right? So metals that precede hydrogen activity series react with acid, and those that follow hydrogen don't react with acid. More active metals react with acid to produce hydrogen gas and an ionic compound. Oh, sorry, let me grab my pen all the time, that pen. So here, see the ion replace the hydrogen, and have the hydrogen by itself on the other side. So in this side we have ion, the other side we have hydrogen. So that is a single displacement. Metals less active than hydrogen show no reaction. Remember, I showed you before, NR, no reaction. So a few metals are active enough to react directly with water. These are called active metals. They react with water to produce a metal hydroxide and hydrogen gas. So we have sodium hydroxide over here, see, replace the hydrogen, and the calcium replace the hydrogen as well. So hydrogen is by itself in the other side. That is a single displacement. So you can predict whether or not reaction occurs just looking to the activity of the metals. So let's practice it together. So aluminum foil is added to iron 2. So if you go to aluminum and the iron, so aluminum is higher, it's have more activity than iron, so will replace aluminum, okay? Here we have the iron to replace aluminum. No, iron is down here, showing that it's less active than aluminum. So aluminum has more activity, so will not be stronger enough to replace the aluminum, so will not have reaction, so NR. Manganese metal is added to acetic acid. So manganese is here and hydrogen is over here. So manganese is stronger and will replace hydrogen, okay? Producing hydrogen gas. Another very important thing is solubility. And it's really important to know some rules. So ionic compounds containing the alkali metals ions and ammonia ions will be soluble. Acetate ion and the nitrite ions will be soluble. Halide ions will be soluble except if they are connected with silver, mercury, and lead. Sulfate ion is the same thing. They are exceptions because they cannot be connected with strontium, barium, and lead. And ionic compounds containing the following ions are generally no soluble in water, like carbonate ion, chromate ion, phosphate ion. So this is not phosphate, that's carbonate. So phosphates, this, and sulfide ion and hydroxide ion. So hydroxide ion, see, you need to look to the exceptions. So if they are connected with calcium, strontium, and barium, so they will be soluble. The same thing for the sulfide with calcium, strontium, and barium, they will be soluble. Okay? So resuming for the ionic compounds of water, we can say all group 1 metals, ions, and ammonium, nitrate, and acetate ions are soluble in water. Ionic compounds lacking those ions are suspected of being no soluble, forming precipitate. We have different tables that give it the information, the same information, different way. Like here, we have the soluble compounds and the no soluble compounds and the exceptions. The same thing over here. So if you have access to those tables, and if you don't know at least the resume of the solubility rules will help you. But if you don't have the table, you need to find a way to keep that in your mind. Like here, barium hydroxide. Remember that hydroxide will be soluble if they are connected with barium. Remember? So that will be soluble. Zinc chloride, so chloride will be soluble. Phosphate will not be soluble, right? So if you look at this table, it will make your life easier. So just press pause in your video and try to do by yourself. Predict the water solubility of the following compounds. We have barium sulfate, potassium sulfate, magnesium sulfate, and iron 2 carbonate. And then also try to write the formula, just practice. Okay, so barium sulfate, they are soluble except if they are connected with silver, lead, and group 2 start from calcium. If you go to your periodic table, barium is not soluble, okay, because they are in the group 2. If you go to potassium nitrate, look at this table. They say that nitrate is always soluble with no exceptions. Sulfate, if you go and look at the sulfate, they are always soluble unless they are connected to silver, lead, and group 2. But magnesium is before calcium, so it will be soluble. Iron 2 carbonate. Carbonate is no soluble unless they are connected with group 1 or ammonia. Is not the case because they are connected with the iron, so it will be not soluble. Okay? Not so hard. And double replacement reaction, 2 ionic compounds in aqueous solution switch anions and produce insoluble substances. Like here, you see here and the chromate, they change place. Now I have barium chromate and potassium chloride. So from the solubility rules, I can tell you that this is solid because chromate will be not soluble. And the aqueous solution, sodium chloride reacts with aqueous lithium nitrate. So they change place over here. And they have sodium nitrate and lithium chloride. And they are both soluble. So we have no reaction, no precipitate. Neutralization reaction is a reaction when you have acid and base. See, hydrogen with no metal and metal with hydroxyl, it's a base. And this is the acid, okay? So they will produce water and salt, like if you have sodium hydroxide and hydrochloric acid. So we're going to produce sodium chloride plus water, okay? So here you have a chance to practice a little bit. Tell me the type of the reaction we have and also balancing the reaction. Okay, so press pause in your video and try by yourself. If you need more time, just press pause. So here, it's easy to see it that we have double replacements because they are changed place. So we have sodium nitrate, zinc, and sulfide. So the equation is well balanced already. Synthesis or combination, so have 2 elements one side and there's one substance on the other side. The composition, so we decompose, we break down the elements. So now I have potassium chloride and oxygen, and now it's well balanced. So combustion, we didn't talk about combustion, but when they have a combustion, we're normally gonna see oxygen on one side and the water and the CO2 on the other side. Single replacement. So it's a single replacement because I can see this magnesium replace the silver. So now we balance the equation. So I have acid over here, and I have a base over here, and I have a salt, and I have a water. So here we have a neutralization reaction. So now it's balanced as well. Okay? And at the end of the chapter, you're always going to find a summary, like a resume. So read, because that helps you to review really fast the most important things over here. Okay, so that's it. That's all. Bye for now.